Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll take a look at Amazon Elastic MapReduce, Amazon's powerful big data platform for processing vast amounts of data at scale. We'll cover common use cases, core concepts like clusters, steps, and jobs, and dive into architecture patterns for data lakes, analytics, and machine learning. Let's get started. Amazon EMR, or Elastic MapReduce, is a fully managed big data platform designed to make it easy to process vast amounts of data quickly and cost-effectively. At its core, EMR is built to simplify running popular open-source frameworks like Apache Spark, Hadoop, Hive, Presto, and HBase, so you can focus more on insights and less on infrastructure. One of EMR's biggest advantages is its flexibility. You can dynamically scale clusters up or down based on your workload using features like auto-scaling and instance fleets to optimize both performance and cost. It's also deeply integrated into the AWS ecosystem, working seamlessly with services like Amazon S3 for storage, AWS Glue for metadata management, IAM for access control, and CloudWatch for logging and monitoring. EMR supports cost-efficient pricing with the ability to use spot instances, helping you save significantly compared to traditional on-prem or even cloud-native on-demand compute models. Depending on your needs, you can choose between running EMR on EC2, on EKS, or using EMR serverless, giving you full control over your operational strategy. It's also built with modern data lake architectures in mind, allowing you to separate storage and compute, take advantage of schema on read, and process data directly in S3. And finally, EMR comes enterprise-ready with robust security features including encryption at rest and in transit, Kerberos authentication, IAM policies, and tight integration with KMS, making it a solid choice even for highly regulated industries. All of this combines to make Amazon EMR a powerful, scalable, and cost-effective platform for big data processing in the cloud. Amazon EMR delivers a powerful combination of flexibility, performance, and cost savings, purpose-built for modern data workloads. First, it offers cost efficiency through per-second billing, so you only pay for the compute time you actually use. This is especially valuable for short-lived jobs or workloads that spike unpredictably. EMR is also elastically scalable, letting you add or remove nodes on demand. EMR is also elastically scalable, giving you the flexibility to grow or shrink your compute capacity based on workload demands. Whether you're running EMR on EC2, on EKS, or using EMR serverless, you can dynamically allocate resources to optimize performance and cost. With EMR on EC2, you can scale clusters up or down and take advantage of spot instances for deep savings, or reserved instances for predictable, steady-state workloads. For containerized environments, EMR on EKS lets you run Spark jobs alongside your Kubernetes applications, leveraging the same auto-scaling and resource management built into your EKS infrastructure. Under the hood, EMR is highly optimized for AWS infrastructure. That means faster cluster provisioning, high-throughput networking, and the ability to choose from SSD-optimized EC2 instance types, all of which contribute to reduced job runtimes and improved processing throughput. For developers and data scientists, EMR is incredibly user-friendly. You can spin up environments with popular tools like Jupyter Notebooks, Apache Zeppelin, or EMR Studio, enabling interactive development, debugging, and visualization right out of the box. And finally, EMR is built with security and compliance in mind. It supports encryption at rest and in transit, integrates with AWS Key Management Service, and adheres to key compliance standards, making it suitable for even the most sensitive data workloads. The Hadoop Distributed File System, or HDFS, is the backbone of data storage in the Hadoop ecosystem. It's designed specifically to store and manage massive volumes of data across a distributed cluster of commodity servers. At its core, HDFS follows a write once, read many access model. This makes it highly efficient for large-scale batch processing, exactly the kind of workloads you'd find in analytics, reporting, or data transformation pipelines. HDFS breaks down files into large blocks, typically 128 or 256 megabytes in size, and then distributes those blocks across multiple nodes in the cluster. To ensure fault tolerance, each block is replicated, usually 3 times, across different nodes. The system is built on a name node and data node architecture. The name node acts as the central metadata manager. It keeps track of the file system structure, block locations, and access permissions. Meanwhile, the data nodes are responsible for actually storing and retrieving the data blocks. Fault tolerance is built in. If a data node goes down, the system automatically recovers the data from one of the other replicas, maintaining availability and reliability even in the face of hardware failures. HDFS is particularly well suited for large files where the overhead of managing metadata is minimal. However, it's not ideal for workloads that involve lots of small files, which can overwhelm the name node with metadata operations. It's also horizontally scalable. As your data grows, simply add more nodes to the cluster. HDFS handles the rest. And finally, HDFS is tightly integrated with the Hadoop ecosystem, serving as the primary storage layer for tools like MapReduce, Hive, and Pig, all of which can run seamlessly on Amazon EMR. EMRFS, or the EMR file system, is Amazon EMR's custom connector that enables seamless integration with Amazon S3, transforming S3 into a first-class storage layer for big data workloads. Unlike traditional HDFS, which ties your data to the lifecycle of a compute cluster, EMRFS decouples storage and compute. This means you can spin up and tear down EMR clusters as needed, while your data persists safely in S3. EMRFS exposes S3 as a Hadoop-compatible file system, so frameworks like Spark, Hive, and Presto can interact with S3 storage, just like they would with HDFS, enabling familiar read and write operations, all without the need to manage disks or worry about cluster storage limits. One key feature of EMRFS is its optional consistency view, which uses DynamoDB to track metadata changes. This helps overcome eventual consistency issues in S3, ensuring your jobs don't miss recently written files, a critical capability in multi-user or parallel job environments. Because EMRFS uses S3 as the backend, you also gain access to virtually unlimited storage without any upfront provisioning. This provides unmatched cost efficiency and scalability, especially when paired with ephemeral compute resources like spot instances. And of course, your data is backed by S3's durability and high availability guarantees, with 11 nines of durability and redundancy across multiple availability zones. Security is also built in. EMRFS supports both server-side and client-side encryption and integrates natively with AWS Key Management Service for fine-grained access control to sensitive data. In modern architectures, EMRFS plays a central role in building data lakes on AWS, enabling schema-on-read processing and interoperability with tools like Athena, Redshift Spectrum, and AWS Glue. Let's walk through two key deployment models for Amazon EMR, each designed to meet different architectural needs, levels of control, and scalability goals. First, we see the classic deployment model, the traditional EMR cluster architecture. In this setup, the EMR cluster is made up of three distinct types of nodes. At the top sits a single master node. The master node is the brain of the cluster. It manages the job scheduling, resource management, and overall coordination across the environment. It's responsible for monitoring the health of the worker nodes and orchestrating the execution of your distributed applications. Below the master node, we have core nodes. These nodes are the workhorses of the cluster. They not only process the data, but also store it locally. Core nodes participate in HDFS, maintaining redundancy and ensuring the cluster's data durability and availability. Further expanding the cluster's computational capacity are the task nodes. These nodes are optional but highly useful when additional compute power is needed temporarily. Task nodes are focused purely on processing. They don't store data in HDFS. This makes them ideal for scaling out your Spark, Hive, or Presto jobs horizontally without impacting data redundancy or storage. These three node types are interconnected, allowing for distributed parallel processing and high-throughput data computation. The cluster interfaces seamlessly with the EMR file system, which connects to Amazon S3. Here you see storage buckets representing persistent storage for input datasets, intermediate processing results, and final output, allowing EMR to scale beyond the limitations of local storage and to persist data even if the cluster is terminated. Now, shifting to the other side of the diagram, we see a more modern approach, EMR on Amazon EKS, or Elastic Kubernetes Service. In this architecture, The traditional concept of a physical EMR cluster is abstracted into EMR virtual clusters running on top of Kubernetes managed resources. Instead of thinking about EC2 instances directly, we think in terms of Kubernetes pods and services. Each EMR virtual cluster is composed of driver pods and executor pods. The driver pods act similarly to the traditional master node. They coordinate the execution of distributed applications such as Spark jobs. They schedule tasks, manage metadata, and handle the overall job lifecycle. The executor pods, on the other hand, are the equivalent of worker nodes. They perform the heavy lifting, the actual execution of the computations across the data. One of the biggest advantages of EMR on EKS is multi-tenancy. Multiple virtual clusters can coexist on the same EKS infrastructure, each isolated but sharing the underlying compute resources efficiently. This model dramatically increases flexibility, allowing organizations to run different Spark versions or different workloads side by side without provisioning and managing separate EC2 clusters for each. In this architecture, EMR Studio and Studio Notebooks integrate seamlessly, providing a fully managed, interactive development environment for data scientists and engineers. Secure, scalable access to the workloads is facilitated by managed endpoints, which allow controlled network communication between the EMR virtual clusters and your VPC environment. Just like in the traditional model, data storage remains decoupled. Buckets are used for storing notebooks, intermediate datasets, logs, and final outputs, ensuring durability and accessibility across application lifecycles. In summary, both deployment models, the classic EC2-based EMR clusters and the newer EKS-based EMR virtual clusters, offer powerful ways to process big data at scale. Choosing between the two depends on your specific operational needs, your team's Kubernetes maturity, and the type of workloads you plan to run. One of the biggest strengths of Amazon EMR lies in its broad support for popular open-source big data applications and frameworks. At the core of many modern data workloads is Apache Spark, a powerful distributed in-memory processing engine. EMR provides a fully optimized Spark runtime, designed to run faster and cheaper on AWS. It's ideal for everything from ETL and data engineering to machine learning and stream processing. For those leveraging traditional SQL-style data processing, Apache Hive offers a familiar interface. Hive runs seamlessly on EMR, supporting both batch queries and integration with data lakes on Amazon S3 through Hive LAP and the Hive Metastore. If interactive querying over large datasets is your use case, Presto, now known as Trino, is a top choice. It allows analysts and engineers to run fast, federated SQL queries across S3, HDFS, relational databases, and more, without having to move data around. For NoSQL workloads, Apache HBase is supported as well. It provides low-latency, real-time access to massive amounts of sparse data, a great fit for time series analysis, recommendation systems, and IoT scenarios. For real-time stream processing, you can bring in Apache Flink through Bootstrap Actions or run it on EMR on EKS. Flink is perfect for processing continuous data streams, powering use cases like fraud detection, real-time dashboards, and anomaly detection. EMR also offers Jupyter and EMR notebooks, enabling data scientists and analysts to prototype and run Spark jobs interactively in Python, Scala, or R. These environments are pre-integrated with Spark and can access data in S3 or HDFS. And for a more integrated development experience, EMR Studio is your go-to solution. It's a fully managed IDE where data engineers and scientists can write code, manage Git repositories, and run jobs, all within a single secured environment. Amazon EMR Serverless represents a powerful evolution in big data processing, offering the performance of Amazon EMR without the operational overhead of managing infrastructure. With EMR Serverless, you can run your Spark and Hive workloads effortlessly without having to provision, manage, or scale clusters. One of the biggest advantages is zero cluster management. There's no need to size your infrastructure, worry about auto-scaling groups, or monitor node health. You simply submit your job, and EMR Serverless takes care of everything behind the scenes, from provisioning compute to shutting it down when the job is done. EMR Serverless is application-aware. It dynamically allocates just the right amount of vCPU and memory for each job, ensuring efficiency and preventing the waste of idle resources. It also scales automatically, whether you're running a small interactive job or a massive parallel ETL job, making it ideal for burst-style or unpredictable workloads. From a pricing standpoint, it's highly cost-efficient. You only pay for the compute and memory you actually use, down to the millisecond. This pay-per-use model makes EMR serverless particularly attractive for spiky or exploratory workloads, where constant uptime isn't required. Startup latency is also minimized. Unlike traditional clusters that may take minutes to spin up, EMR serverless can launch jobs much faster, enabling quicker development cycles and interactive querying. It integrates seamlessly with Amazon S3, allowing your data to remain in your data lake. It also works with the AWS Glue data catalog, so your metadata is consistent across tools and workloads. For data scientists and developers, EMR serverless simplifies experimentation and lowers the barrier to entry. You don't need to be an infrastructure expert. Just write your Spark or Hive job, submit it, and let EMR serverless take care of the rest. Amazon EMR provides multiple deployment options to fit a wide variety of analytics workloads, team preferences, and architectural strategies. The three primary modes are EMR on EC2, EMR on EKS, and EMR serverless, each with its own strengths and trade-offs. Let's start with EMR on EC2, the most traditional option. This deployment model provisions a cluster of Amazon EC2 instances, where Yarn manages resources across a fleet of nodes. It's ideal for users who want full control over their environment. You can choose the exact instance types, configure the operating system, install custom libraries, and use Bootstrap actions to tailor the cluster to your needs. It's a powerful setup for long-running jobs and highly tuned workloads, where you can mix on-demand, spot, and reserved instances. However, this model comes with higher operational overhead. EMR on EKS brings EMR into the world of containers. Here, your jobs run as Kubernetes pods inside your Amazon EKS cluster. This model is great for organizations that are already investing in Kubernetes and want to centralize their compute resources across multiple teams or workloads. With EKS, you get faster job startup times and container-level isolation, which improves security and resource efficiency. It's also easier to integrate with modern CI/CD workflows. Finally, we have EMR serverless, the most simplified deployment model. With EMR serverless, there's no infrastructure to manage. You don't need to worry about provisioning nodes or configuring auto-scaling. Jobs start in seconds, scale automatically based on demand, and shut down once the work is complete. This is ideal for ad hoc analytics, bursty jobs, or when you want to prototype and iterate quickly. You only pay for the compute time your job uses, down to the second. While it offers the least amount of customization, it delivers the highest agility and the lowest operational burden. So whether you're looking for deep customization, container-native execution, or a fully serverless experience, Amazon EMR has a deployment option that fits your needs. Amazon EMR is purpose-built to integrate seamlessly with both modern data lakes and enterprise data warehouses, making it a foundational piece in end-to-end analytics architectures on AWS. At the heart of this integration is Amazon S3, the de facto data lake storage layer in AWS. Through EMRFS, EMR can treat S3 as a Hadoop-compatible file system. This means you can directly store raw, semi-structured, or transformed data in S3 and run Spark, Hive, or Presto jobs over it without managing persistent storage, giving you massive scalability and cost efficiency. It also integrates natively with the AWS Glue data catalog, which serves as a central metadata repository. This makes it easy to share table definitions and partitions between EMR, Amazon Athena, and Redshift Spectrum, enabling a consistent query layer across services and minimizing redundant metadata management. EMR also supports query federation, allowing Spark and Hive queries to seamlessly pull in data from multiple sources, including S3, relational databases like RDS and Aurora via JDBC, and even Amazon Redshift. This means you can perform analytics across your entire data landscape without moving data. For tighter coupling with Redshift, EMR supports optimized copy and unload commands, enabling efficient, high-speed transfers of large datasets between EMR jobs and Redshift warehouses. Perfect for ETL workflows or backfilling analytical data marts. EMR also supports advanced data lake table formats, such as Apache Hudi and Delta Lake. These enable ACID transactions, time travel, and efficient upserts, bringing warehouse-like capabilities to your S3-backed lake, a critical requirement in modern data lakehouse architectures. And since EMR, Athena, and Redshift Spectrum can all access the same Glue catalog and S3 datasets, you gain a highly interoperable ecosystem that supports batch, interactive, and federated querying patterns. One of the key advantages of Amazon EMR is its ability to scale elastically, giving you the power to handle workloads of any size, from a single notebook job to multi-petabyte batch processing pipelines. First, when running EMR on EC2, you can enable cluster auto-scaling. This allows EMR to automatically adjust the number of EC2 instances based on predefined rules or resource utilization metrics like CPU, memory, or yarn resource consumption. You can scale up when demand spikes and scale down when workloads taper off, optimizing both performance and cost. EMR supports both instance groups and instance fleets. Instance groups offer a simpler scaling model, while instance fleets provide more flexibility, letting you mix on-demand, spot, and reserved instances across different instance types. This is especially powerful when using spot instances to reduce cost for fault-tolerant jobs. Within the cluster, task nodes, which are responsible for running transient jobs, can be added or removed dynamically. This means your core nodes stay stable, while your compute layer can flex with workload demands. EMR uses Yarn as the underlying resource manager, efficiently allocating CPU and memory across distributed applications. Yarn ensures that Spark, Hive, or other workloads share resources optimally, avoiding bottlenecks and maximizing throughput. If you're running EMR on Amazon EKS, your Spark jobs execute as Kubernetes pods and can take advantage of Kubernetes native auto-scaling. You get granular, pod-level scaling across shared infrastructure, ideal for containerized environments. And with EMR serverless, scaling is fully managed by AWS. There's no cluster to manage. Compute is provisioned at the job level, scaling up or down automatically based on demand. This is perfect for bursty, on-demand workloads, or when you want to focus solely on your application logic. EMR supports encryption both at rest and in transit. For data at rest, you can use KMS or bring your own custom keys. Data in transit between nodes or from EMR to services like Amazon S3 is secured using TLS. This means your data is protected throughout its entire lifecycle, from ingestion to analysis to storage. Access control is handled through tight integration with IAM. You can assign granular permissions to users, roles, and services, ensuring that only the right entities can perform specific actions on your cluster and data. For environments requiring additional authentication, EMR supports Kerberos integration. This provides strong, ticket-based authentication between users and Hadoop services, adding another layer of protection against unauthorized access. EMR also supports Amazon VPC, allowing you to launch your clusters within a logically isolated network. You can configure private subnets, route tables, and security groups to fully control how your cluster communicates with the outside world. If you're building a secure data lake, EMR integrates seamlessly with AWS Lake Formation, allowing you to manage fine-grained permissions on datasets stored in Amazon S3. Lake formation policies can be enforced at the table, column, or even row level when accessed through EMR with Apache Hive or Presto. To simplify security best practices, EMR provides managed security configuration templates. These reusable configurations let you enforce consistent settings, such as encryption, authentication, and logging, across all your clusters. Monitoring and compliance are critical too. EMR integrates with AWS CloudTrail and Amazon CloudWatch, enabling detailed audit logging and operational insights. You can track API calls, user behavior, and system events, all of which are essential for security auditing and incident response. Finally, for teams using EMR Studio or EMR Serverless, EMR ensures that user sessions and job executions are securely isolated. Workspace permissions are role-based, preventing data leakage between users and ensuring compliance in multi-tenant environments. When considering Amazon EMR for your data processing workloads, it's important to understand the underlying pricing model to manage costs effectively. First, EMR offers per-second billing. This means you are charged only for the exact time your cluster is running, with a 1-minute minimum. It's also important to note that EMR pricing is modular. You are charged separately for different resources. That includes the cost of the Amazon EC2 instances that power your cluster, the EBS volumes attached for storage, and the EMR service itself. When you deploy EMR on EC2, your pricing is based directly on the number and type of EC2 instances you use. Irrespective of the instance type chosen, your costs scale according to the resources your cluster consumes. For customers who prefer a serverless, hands-off model, EMR Serverless offers a different pricing structure. Instead of paying for cluster infrastructure, you are billed based on the actual compute that your Spark or Hive workloads consume. Storage for intermediate and output data is also billed separately. If you choose to run EMR workloads on Amazon EKS, pricing works slightly differently. In this case, you pay separately for the EKS cluster resources, such as the underlying EC2 instances or AWS Fargate, plus a small per virtual cluster management fee that covers the EMR control plane functionality layered on top of Kubernetes. Keep in mind that data transfer costs can also affect your overall spend. Standard AWS data transfer rates apply, particularly when data moves across different regions or services outside of your VPC. Finally, some additional features and integrations can impact your bill. Services like EMR Studio for notebook-based development, Amazon S3 storage through EMRFS, and EMR managed scaling for automatic right-sizing all provide tremendous value, but should be factored into your cost estimates based on usage patterns. While Amazon EMR offers tremendous scalability and performance for big data workloads, managing and optimizing your costs is just as important as tuning your jobs. First and foremost, spot instances are your best friend for cost savings. You can use spot instances for task nodes in your EMR cluster to handle transient compute jobs. Since task nodes don't store important cluster metadata or HDFS data, they can be safely interrupted and replaced. Second, right-size your instance types. Don't pay for resources you don't need. If your Spark jobs are memory intensive, go for memory-optimized instances. If they're I/O bound, choose SSD-backed storage. Analyze job profiles and tune your instance selection accordingly. Cluster auto-scaling is another essential tool. By dynamically adjusting your cluster size based on metrics like yarn utilization or task queue length, you ensure that you're not overpaying for idle compute resources during low-load periods. If your workloads are intermittent, think development jobs, exploratory analysis, or ad hoc ETL, consider EMR Serverless. It completely removes the need to manage infrastructure, and you're only billed for the compute and memory your job consumes while it runs. Don't forget to automate cluster shutdowns. Unused clusters are silent budget killers. Use EMR's built-in settings to terminate clusters automatically after job completion, or implement scripts and lifecycle hooks to tear them down after a set period of inactivity. Store your data on Amazon S3 using EMRFS instead of on local HDFS. This allows you to create short-lived clusters that process data and terminate without needing persistent storage attached to your compute nodes, massively cutting storage costs over time. At the heart of EMR monitoring is Amazon CloudWatch, which automatically collects and aggregates key metrics like CPU usage, memory, disk I/O, and HDFS utilization. These metrics can be visualized in real time, and you can easily set up alarms to alert you when thresholds are breached, helping you take proactive actions before issues escalate. For a deeper dive into your applications, EMR aggregates all system and application logs to Amazon S3. This includes logs from Hadoop, Spark, and system daemons. Persisting logs in S3 means you can analyze them later or stream them into services like Amazon OpenSearch or third-party observability platforms. EMR also supports Ganglia, a widely used open-source monitoring system. When enabled, Ganglia gives you a granular look at individual node metrics and job-level behavior, particularly useful for debugging performance bottlenecks. You can also access the Yarn Resource Manager UI, which provides a real-time dashboard of job queues, resource allocations, and container statuses. This is particularly helpful when you're managing concurrent jobs or tuning resource distribution. For Spark applications, the Spark History Server is your go-to tool. It offers an interactive web interface to review past job executions, visualize DAGs, examine job stages, and understand execution timelines, critical for diagnosing job-level inefficiencies. AWS CloudTrail complements CloudWatch by auditing all EMR API activity and user actions. This is vital for tracking changes, understanding who did what, and meeting compliance needs. Finally, EMR is extensible. It supports integration with third-party observability like Datadog, Prometheus, or OpenTelemetry, giving you the flexibility to incorporate EMR insights into your broader monitoring ecosystem. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.